All right, let's dive right into this explainer. Today we're taking a fascinating factory tour. We hear all about massive generative AI models, right? How they can write, code, and paint for us, but how often do we actually look at the gears turning underneath? Well, today we're going to strip away the scale and all the mystique and see exactly how these powerful systems are built from the ground up, starting from a single, tiny calculation.
Here's our blueprint for today. We'll be looking at the atomic unit of AI, how AI actually learns, built for sight and sound, taming the AI chaos, where AI does its thinking, and finally, the cost of big math. We are literally going to build an AI from scratch, scaling all the way up from a single artificial neuron to the billions of parameters that require entire data centers just to turn on.
Starting off with Section 1, the atomic unit of AI, starting small. We're kicking things off right on the assembly line with the absolute smallest, most foundational piece of the entire system.
If you strip away all the hype, every single AI out there is built on this one thing, the artificial neuron. And it's actually a mathematical abstraction from way back in 1943. It's pretty straightforward. It takes a set of inputs, multiplies them by some learnable weights, adds a bias number, and then passes that result through a nonlinear activation function. Think of that function as a mathematical gatekeeper that decides whether the signal should pass forward or not. When you stack millions of these simple artificial neurons side by side into layers, and then string those layers together in a sequence, you create a multi-layer perceptron. Every single inference made by modern models is really just this one calculation, repeated across massive matrices.
But, to get to modern AI, early networks hit a massive roadblock. This is sort of the recurring villain of our story, known as the vanishing gradient problem. When networks get really, really deep, the learning signals, which we call gradients, have to pass backward through a ton of layers. Because they're multiplied together, if those numbers are even slightly smaller than 1, they shrink multiplicatively towards 0. The result? The early layers of the network essentially freeze up. The foundation literally never learns.
And this is a brilliant illustration of how researchers actually defeated that villain. Look at the early default, the sigmoid function. It squashed inputs into a really tight range, meaning the slope flattened out, which directly caused those vanishing gradients. But then came ReLU, introduced around 2011. It is almost insultingly simple. If a number is negative, bam, make it 0. If it's positive, leave it alone. Because the positive side never flattens out, gradients survive through incredible depth. Today, a smooth refinement of this called GELU is the default inside the massive transformer models we all use. That one simple math fix completely changed the game.
Moving on to Section 2, how AI actually learns, the engine. Now that we have the basic architecture down, we need to look at the learning engine driving the whole machine. How exactly do billions of weights tune themselves?
Well, the process is called backpropagation, and it's this incredibly elegant three-step loop. First up, the forward pass. Data moves left to right through the network, makes a prediction, and we cache all the intermediate values. Second, the backward pass. We look at how wrong the prediction was and apply the chain rule of calculus right to left. This traces the error backward to figure out exactly how much to tweak each parameter. Finally, step 3, we update the weights. Training a massive model like GPT-4 is literally just this 1, 2, 3 loop, executed over hundreds of billions of parameters, trillions of times. So, the absolutely crucial point here is that backpropagation is just a specific application of what mathematicians call reverse mode automatic differentiation. Why is this the absolute engine of deep learning? Because instead of nudging every single parameter one by one just to see what happens, which would take, forever for a billion parameter model, reverse mode autodiff gets the exact gradients for all parameters simultaneously. It does it in one perfectly organized backward sweep. And the kicker? It does this at only about twice the computational cost of a forward pass. This specific math trick is the literal reason tools like ChatGPT can even exist in our lifetimes.
All right, Section 3, built for sight and sound, specialized machinery. Next up, we take that basic engine and we shape it to handle specific real-world tasks using structural assumptions. We call these inductive biases. This head-to-head comparison perfectly shows how different architectures solve totally different structural problems. Take convolutional neural networks, or CNNs. They assume spatial locality, which just means pixels close together form larger shapes. They also assume translation invariance, meaning, hey, a cat is a cat no matter where it's sitting in the picture. They scan images like a sliding magnifying glass, making them the absolute kings of computer vision. On the flip side, we have recurrent neural networks, or RNNs. They assume sequential dependence, meaning the present depends on the past. They maintain a hidden state that updates over time, which actually made them the early pioneers for text and speech generation, way before transformers came along.
Section 4. Taming the AI Chaos. Quality control. So, we've got these incredibly deep networks and super powerful learning algorithms. But how on earth do we stop these massive systems from just blowing up, or lazily memorizing their training data?
To stop that chaos, we deploy a standard stabilization toolkit. Think of it as our quality control department. Things like weight decay keep the math simple by actively penalizing large weights. Dropout is wild. It literally zeroes out random neurons during training. This forces the network to build redundant, robust pathways instead of just relying on one specific feature. We also use normalization layers to constantly rebalance the math inside the network so values don't swing wildly out of control. This whole grab bag of techniques forces the network to learn actual generalized signals instead of just memorizing the noise.
Now, this right here is another absolute game changer. Remember our villain, the vanishing gradient problem? Well, residual connections essentially give those gradients an express lane. Instead of a layer entirely replacing its input with a brand new calculation, it just computes an additive correction to it. That little plus sign in the equation means information and those crucial learning gradients can skip past the heavy multiplications entirely untouched. This single elegant tweak allowed feasible network depth to jump from just tens of layers to hundreds of layers practically overnight.
Which brings us to Section 5, where AI does its thinking. The brain's geography. Let's move to where the AI actually thinks and see how it builds an understanding of discrete concepts, like human language.
Words don't natively do math. The word cat isn't inherently closer to dog than it is to car. But through training, AI assigns each word a dense list of numbers called an embedding. Essentially, the AI maps language directly into geometry. Because words used in similar contexts slowly drift closer together in this geometric space, we get these wild aha moments. Check this out. If you take the mathematical vector for king, subtract the vector for man, and add the vector for woman, you mathematically arrive right at the vector for queen. It's incredible. Semantics literally become geometry.
And that leads us to a profound realization about generative AI. Whether it's writing an essay or drawing a stunning image, generation quality is representation quality. A model generates well exactly insofar as it has internalized a clean, geometric representation of our world. Every spectacular sample you've ever seen is simply the model smoothly navigating and reading out from this beautifully organized coordinate system, which researchers called the latent space. Finally, Section 6, the cost of big math, the power plant. Let's plug this whole massive machine into the wall. Ideas in this field are heavily rationed by arithmetic, and we really need to look at the sheer hardware required to run it all. Now, you might be wondering, why don't we just train these models on regular computer processors, CPUs? Well, because a CPU is kind of like a few brilliant professors, highly optimized for complex, branching, serial logic. But deep learning craves throughput. It wants oceans of identical, repetitive matrix operations without any branching. A GPU, on the other hand, is like thousands of factory workers acting in perfect unison. Originally built to render millions of pixels for video games, the GPU's massively parallel architecture turned out to be the exact engine generative AI needed. But even using GPUs, prepare for a little sticker shock here. Training what is considered a relatively small model today, say a 7 billion parameter model, requires at least 112 gigabytes of memory. And that is not to store the training data. That is just to hold the model state during training. Let's actually break that math down. Every single parameter in that model demands 16 bytes of memory during training. You need 2 bytes for the weights, 2 bytes for the gradients, 4 bytes for a high-precision master copy of the weights, and 8 bytes just for the optimizer to track its momentum. When you multiply 16 bytes by 7 billion parameters, you hit over 112 gigabytes. If you scale that up to a frontier 70 billion parameter model, training states rapidly push over a terabyte. This is exactly why training state-of-the-art AI requires not just a big computer, but entire data centers, and literally billions of dollars all wired together. As we step off the factory floor today, consider this one thought. We've seen that these models flawlessly capture the statistics of our world by embedding language and images into geometric math. But our world's data isn't exactly perfect, is it? If these vast coordinate spaces perfectly encode our history, what happens to our generated future when human flaws, stereotypes, and biases are mathematically hard-coded right into the machine? It's a fascinating, and maybe slightly terrifying, mathematical reality that we're only just beginning to grapple with. Thanks so much for joining me on this explainer. Keep learning, and I'll see you next time.